you. Okay, next topic is backpropagation. So what is backpropagation? See, this is what your neural network model. Um, One second, I will draw the diagram once again. Sorry, if this is not looking good, I'll just put the neurons in a big so that you can. This is your input layer, okay? Input one and input feature, okay? This age and income, you just think that way. This is your hidden layer neuron. Hidden layer neuron. In this case, we have two neurons are in output layer. This is your output layer. This is your hidden layer. This is your input layer. Here, this one is connected to this one, and this one also connected to this one. Okay. And this one is connected to this one, and this one is connected to this one. And we are left with another neuron. This neuron will get connected to this one, and this one will get connected. Why it is getting, that is how it works. Okay. And then, yeah, this one should get connected to this one. There is no gap. Okay. Everything, all the neurons should have the link with every other neuron. And here, I just said this is a weight one. This line is called a synapse. It's a network, right? This is a cable. It's kind of a cable connection. Right? The synapse. We call it the synapse. So weight one is 0.15. Let's assume that's a 0.15. And this line is, weight two. I just call it a weight two. And 0.20. Let's say, hypothetically, we'll put some values. Okay. This line, each connecting line has its own weights. It will have weights. Okay. 0.25. And this is weight 4 and 0.30. Let's assume that, okay, these 0.15, 0.20 for weight 2 and weight 3 is 0.25 and weight 4. So how did you arrange? This is, some imagery numbers. Okay, the input value is 0.05 and here line is 0.10. And here, even between the hidden layer to output layer, you have the synapses. This line is called a synapse, and I call, so here we have used weight 1, weight 2, weight 3, weight 4. Here weight 5. This is 0.40. The weight is let's 0.40. And this is this line is weight 6. Okay. Sorry, this line is, okay, this one is your weight 6 and 0.45. I just call this a weight 7. This is going to be zero point 0.5. Sorry, I just say, W5, W6. W6 is going to be 0.45. And W7 is going to be 0.50. And W8 is going to be 0.55. And I told you one more neuron, right? Bias. Bias should be there. Bias will be introduced between the hidden layer and output layer. Okay, sorry. Each hidden layer and output layer will have the bias. And this one will be get connected to this one, and this one will get connected to this one. And similarly, this one will get connected, this one will get connected. So bias is kind of, you just think about the intercept in neural network. Sorry, the linear regression model, right? So the intercept, I told you, um, so there are cases uh, if you don't advertise anything, right? So what is the sales? So in that case, the estimated average value, average sales values obtained with the help of the intercept, right? It's something like intercept, you just think that way, the bias. Okay, so here in this case, I just say the bias is 1 here, the value of the 1, and the weight for this line is, let's say 0.35, okay, 0.35. And for this, the weight is, it's hypothetically 0.60. Okay, 0.60. So here the values are, let's say, this is your age and income. This value is passed to this one and it is passed here. And then the output of this value will be passed to this one. The output of this one will be passed to this one. How the output of this one will be computed? There are two steps, 1 and 2, right? Z is equivalent to this value, weight 1 into 0.05, weight 2 into, so weight 1 into 0.5 plus weight 2 into 0.20, right? And whatever the value, so what is weight 1? Weight 1 is 0.15. Weight 2 is 0.20. Multiply, whatever the value you get it, that is what you is that. Once you solve this thing, right? Once you compute the value, that will get stored here. And then the activation function, 1 divided by 1 plus e to the power minus z. In this case, I have used the sigmoid activation function for the sake of simplicity. Okay. E to the minus, right? The first step is this one. The second step is this one. The output of this one is your the hidden layer's first neuron's value. This value will be passed to this one. Even this value will be multiplied by this weight 5. So this value into the weight 5 is 0.40 and this value into the weight 0.45. And that value will be emitted to this one. Got it? So the values are flowing from the input layer to hidden layer to the output layer. Hence, it is called as a forward pass. Forward pass. It is also called as multi-layer perceptron. Multi-layer perceptron. Multi-layer perceptron. Got it? Okay, so now the output layer, we have two neurons. So this is what my output layer, right? We have two neurons here. And here, how do we find out the cost here? For example, here you have net H1 and this is your output value, right? Here also the two steps, like how it carries out, two tasks as part of each hidden layer neuron. Even in the case of output layer, it carries out two tasks. It takes the immediate weight and it takes the product of the immediate weights and then the preceding neurons output value. So this one into 0.40 plus this one into 0.45, it will multiply this and that is what your estimated outcome value. For example, your actual predicted value, see actual value is 0.01, okay? And the predicted value is 0.75, something like that, okay? 7536, something like that. If you subtract this your actual value, the predicted value, you will get an error, right? This is what it is. So E1, so error 0, 1. For this neuron, each neuron you will get error, right? So this is the error. And what is the probability customer will churn? What is the probability the customer will not churn, right? So E01 is going to be 1 by 2 into, you remember, mean, mean squared error, right? You take the average of everything, right? So this is your actual minus predicted whole square. Even similarly, this layer also, you have the actual value and then the predicted value. So 1 by 2 minus the same thing, actual minus predicted whole square, E1 E2. If you add these two values, that is what your total error. E1 plus E2 is your total error. If I add, for example, in this case, E1 plus E2, if I add this together, for example, my E1 is, if you subtract 0.75 from 0.01, what you will get? Let's say you get 0.27, E1 error, 0.2748, something like that, plus the E2 error is something like 0.23, 0.023, something like that. It will give you the total error is 0.29, 0.29837. So if somebody asks you, hey, you trained the neural network model, can you give me the accuracy? What is the error? What is the cost? Remember this. This is what cost. Okay. The error is, instead of using the term error, they use the term called a cost. Okay. So the cost is 0.2987. Now, when you go back and tell your on-site manager who is sitting in USA, he's the one coordinating with you at offshore, and then, hey, what is the cost? You say 0.29. He says, no, no, customer is not happy. You need to reduce the cost. Reduce the cost means, what does that say? Reduce the error. Okay, how will you reduce the error? How will you reduce the error? So in the linear regression, logistic regression, I told you, right? Let's say you trained your model. The model, in the case of binary classification, accuracy we use it, right? In the case of linear regression model, what is that you use it? Yes, Soundarya, Soumya are correct, right? Yeah. So in that case, linear regression model error, right? Root mean squared error. The lesser the root mean squared, the better the model. That means lesser the error, the better the model predicted accuracy is good, right? But in that case, as pointed out Soundarya, what I told, probably you can find out the features that are having higher predictive power. Feature selection, you need to do it. What is feature selection? How many of you remember it? Yes, 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 yes. Very good. Feature selection is, we can use RFE, right? I explained about RFE, recursive feature elimination. So in that case, it finds out the features or the input features that are really helpful in terms of predicting your outcome very well. If you include only those features recommended by RFE, we have even the random forest, right? Feature importance, we have something else. With that also, if we are able to identify the input features that are really helpful in terms of predicted outcome variable, include only those input variables or input features that are having higher predictive power. Rest of the features, input features, simply you can drop it. That is one way of improving your model accuracy, right? When it comes to neural network, what is this? Here also the same step, but in addition, what they do is, what they say is, we have something called forward pass and backward pass. What they say is, hey, send this error back, right? Send this error or this error, right? So for example, here you are getting some value, or let's say 0.27 and 48481, right? This is the error for this one. And send the error back to this guy. See, it's something like, guys, in our life, let's you are somebody is asking you to find out the total. uh, let's say I've given a full scape paper. In the paper, let's say 100 lines are there. Each line, the total, say, sorry, the sales value is there. If I ask you to compute it, to do that role, there is a chance that you may tend to make a mistake, right? That is your cost, error. Error is nothing but cost. And you come back and tell me, sir, this is the ban. And I ask you, what is the cost, error? How much error you made? So you say, maybe maybe some plus or minus 2% error will be there, sir. Since you asked me to count it, to sum it, I did it in a pretty fast manner. Okay. But you say, there will be 0.2769 error will be there. And okay, minimize error. What you do? Again, you go back, take the paper and start from the beginning. You will do the total again, right? So in this case, the error for the output layer will be sent back here. This one will be sent to this one, and this one will be sent to this one. This one will be sent to that. So the error will be sent back, right? So the whole idea of this one is, change the value of the weights. See, this error is obtained based on the weights for each layer, right? Each synapse's weights. See, this error is fully depending on this one, right? Isn't it? So I will show you with calculation tomorrow, okay? So this error is depending on the previous weights, previous layers weights. So what you do is change the values of weights and see if you can reduce the error. If you change the values of the weights with different values, See, what I say is blindly, listen, I'm telling you, hey, guys, you change the values of weights and then try to reduce error. What you do? Yeah, instead of 0.40, you make it 0.35, and here 0.15, you make it 0.12. So you try the different weights and then substitute the values in this formula, right? In this formula, and then you apply the activation function, and then that value will be passing it here, and finally you will get this value. And again, you compare, the after changing the weight, what is the error? Again, you do the same thing, but error reduced, but not much. I want to reduce. Again, you change the weights. So iteratively, that is called iteration, right? Do it again and again. So, change the weights repeatedly and see if you can reduce the error. Okay. So in that case, if I change the values manually or based on my intuition, right, based on my in the intuition blindly, what will happen? You will end up, changing the values throughout your life, right? Let's say you are changing to 3.5 and 0.25, the error will be still more than this one. Let's say more than this one, or the error not reduced, something like that. You will keep changing, changing, changing. So, there is a mechanism called back propagation. So in the case of back propagation, they use something called gradient descent algorithm. The interview, they'll ask you what is back propagation. In the case of back propagation, the whole objective of back propagation is to minimize the error or the cost of my model. So what back propagation does is it uses an algorithm called gradient descent algorithm. 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 It's a very interesting one. So this gradient descent algorithm, what it does is, with the help of the gradient descent algorithm, what will come up with the optimal values for these weights. With that weights, with that changed weights, if you fit the model, you will see with the help of this model, the algorithm, gradient descent algorithm, right? This algorithm basically helps us to minimize the cost by coming up with the optimal values for the weights. See, it's something like in your life, right? Let's say every month you look at your bank statement. And if I ask you, hey, cut down the cost, cut down the cost. So where should I cut down? Where should I, there are, so let's say you are a money on investment, the advertisement, what will happen? Your competitive, all your customers will go to your competitor. You will lose the business, right? It doesn't mean if you cut down the advertisement cost, your sales will grow, right? Since expense is going down, but again, you need to come up with the optimal value. It should not be more, it should not be less. That is what the term optimal tells. Don't spend too much, don't spend too less, spend optimally. In between these two, you spend. So the gradient descent algorithm helps us to find out the optimal values for the weights, right, till we get the minimum cost, right? So it will try to reduce the error as less as possible. That is the whole objective of gradient descent. The gradient descent algorithm, it uses chain rule and then power rule and all. Okay, yeah, as requested by Sarah and Praveen and Deepa, will take it up tomorrow. It involves a lot of derivation. We will discuss about that in tomorrow's session. Okay, tomorrow don't miss out. It's a very important topic, guys. The